So a couple of weeks ago, Ivan dropped a message to both Cedric and myself that he would be passing through Prague and would be interested in giving a presentation at our institute, and we were happy to invite him to come here and do just that. To introduce Ivan, Ivan did his PhD, completed his PhD in 1995 at the Institute of Geology, Geophysics and Mineralogy of the Russian Academies of Sciences in Novosibirsk. After that, he had several postdoctoral stays in Europe, one in France, in Villefranche-sur-Mer, and actually two of them at the GFZ in Potsdam. And since the year 2008, he is the head of the Laboratory for Seismic Tomography at the Institute of Petroleum, Geology and Geophysics, which I've heard is the same institute as the one he did his PhD, just under a different name, of the Russian Academy of Sciences, again in Novosibirsk. His scientific work is centered on seismic tomography, mostly but not only travel time body wave tomography, at all kinds of different scales and applied to all kinds of different regions and tectonic settings. He has also written a number of well-known tomography codes, among them the rather well-known Lotus code. And in recent years, his scientific focus was shifting more and more towards volcanic systems, where he tries to image the feeding system and the plumbing system using seismic tomography. And with that, I'll hand over to you, and happy to have you here.
Okay, thank you very much, Christian, for this kind presentation. Before starting my talk, I would like to make a very important statement that I needed to do, because now we live in a very terrible time of this cruel war, and I want to express my appreciation and my solidarity with Ukrainian people who heroically resist against this invasion. I would say honestly that it is not easy for me to say these words, first of all, because I'm a part of this Russian community, Russian society, which greatly support this war. You cannot imagine how people become crazy in Russia. I'm talking with people, just simple people like you from academy, society, and many people support this war. And it is really impossible to convince them that this is criminal. And I want you to know that not all Russians like this. So not all Russians support this war. And I hold also some responsibility because I'm part of this society. But from the first day of this war, I declared my very clear that this is a criminal. This is very bad for our country, for all the world, and of course for Ukraine. And fortunately, Ukrainian people are so brave and so strong that they can resist against this war, and I really appreciate how they resist. And so I would like you to know that I'm against this war, and it was not. Okay, now science is presumed to be out of politics, so we need especially science regarding the earthquakes, regarding the volcanoes. We need to do our science regardless of all these political problems. We should share our data. Otherwise, it is impossible to work on earthquakes or on volcanoes sitting in one place, in one country. You become very limited. You should share your data, you should share your experience, you should share your algorithms. And one of my main purposes of visit to here to Prague is to share my experience, to show the data that we hold in our group, and to say that all this data that I will present in this talk are available for anybody who is interested to work. All the algorithms that we developed are available for any of us. We are ready to share these algorithms with you, and we would be happy to collaborate. Also, I think that this nightmare regarding this war will end and this regime will crash and Russia become a civilized country, and you will be able to, again to come to our country, to Kamchatka, to visit this absolutely amazing places of Kamchatka and the Kuril Island, and we will deploy some joint experiments there all together with you. But by now, I think we needed to continue our collaboration, to work with the data which are available, to share our experience, and I hope after this talk we will establish some links with you. I really hope on it. So after such presentation, I would like to start. So in this talk, I would like to present our results regarding Kamchatka. And Kamchatka, you know, this is subduction zone, and the subduction zone is a very complex system of interaction of different mechanical, thermal, chemical processes that finally produce some magma activity at different depths, which finally make some eruptions. And to understand this is extremely complicated system. This is a multi-scale system regarding the time and scale, so the processes may occur for millions of years, or for 100 years, and even for seconds. So to understand, and also it might be on scale of 1,000 kilometers if we are talking about subducting slab, or it might be in 100 kilometers if we are talking about mantle wedge, or it might be tens of kilometers, 1 kilometer or 100 meters. So all the scales are important to understand the mechanism of magma generation and the eruption production. Therefore, we needed to have instruments which are able to work on all of these scales. And seismic tomography is an excellent tool to look at the deep to the earth on different scales. And in this talk, I will try to present this is quite of methodological approach to show that we are able to work on all of these scales from 1,000 kilometers to first kilometers and even smaller, and to present some series of results that from a global scale to a very small scales. Okay, so this is Kamchatka. You know, of course, its geographical position. It is at the edge of the Pacific plate. There is an edge here where the plate is broken, and there is the Aleutian plate, which has a kind of oblique and even horizontal lateral movement of the plate in this location, but this is more or less orthogonal subduction that occur beneath subduction, and there is a Kamchatka segment, and there is a segment of the Kuril Island. So in this talk, I will talk mostly about Kamchatka, but we also work on the Kuril Islands as well. And we also have some results on the Aleutian Island, but unfortunately I will not show it. But if you are interested, there are many different results on Katmai, on Okmok, on Atka, on Spur, on Redoubt. So I would be very happy to show these results to you, maybe next time or tomorrow, in any kind of. So this is Kamchatka, and I would say that Kamchatka is a very hard region for exploration. So, there is very little roads in this area. So most of these areas are really wild and empty, and there is no way to come there except for helicopters for very long walking from the nearest road. So, and logistically, it is extremely hard to work there. So before 2012, there were some permanent stations which are deployed by a geophysical survey. And I would say that this is a real challenge to install the stations. If you saw how they are installed in absolutely empty place, you should climb for the whole day to reach the station, and you should climb with batteries, and you should change this battery from time to time, and the weather condition is very difficult. So these people who hold this network, which is shown here by blue triangles, is real heroes. And all of the stations are available online. So if they put the stations, they transmit the data most of the stations are telemetric stations, and they keep this information, they store this information for dozens of years. So this data is really unique, and this data is available. So if you want to work with them, I think it is possible to use this data. But you see that the distribution of this data is not optimal. So these stations are mostly oriented to explore the seismicity or the volcanic activity. And in most cases, they are not suitable to explore the structure which is most interesting for us. And to make such seismic tomography studies, we needed to deploy some additional stations, some portable networks, which can be of different scales. So we started from the Avacha region. This is Avacha group. Then we did every year, we come to Kamchatka, we deploy our stations in one place, then we remove these stations from this place and we move it to another place. Sometimes these experiments are very large, sometimes they are smaller. So sometimes in some years we deploy maybe 2 networks, but every time, every experiment is a kind of adventure. So every time we needed to think about the logistics, which is very complicated. And of course, we needed to find some funds to cover all the expenses. I will just show some photos with the deployment of stations. You see that we work in many different conditions. And we use such an excellent track that can pass off-road track, but not always it can pass. But this is a Kamaz, which is a very good solution for many places. This is on Tolbachik, but in most places we needed to fly with such light helicopter. We keep it in our campus, so in our camp. So it's a good solution, but quite expensive. But in most cases we needed to walk just by foot to climb with the batteries, which are quite heavy. And the most important skill for geophysicists in our group is to dig very quickly the holes, because otherwise the helicopter cannot wait us. So such people who can do it are very appreciated. And finally, this is from our last field trip. It was like a mission impossible, and we really climbed on some rocks and jumped from helicopter and from the boat and with the quads, and all of them was in the background of eruption of a volcano, so it was really mission impossible, like or James Bond adventure. So it was funny. It was really funny. This year we will go to the same place to make an empty profile and to remove all of the stations. Yes. Okay, so now return to our tomography from these nice pictures to our tomography. This is our mantle wedge. This is a system of magma plumbing system, which is initially generated from the slab. So we need all of these elements. We need the shape of the slab, which strongly affects the volcanism. We need the structure of the mantle wedge. We need the structure of the entire crust, and also we need the detailed structure of the uppermost part of the subduction. For this, here I list some algorithms, some schemes that we developed in our group. We work on the active source tomography, we work on the ambient noise tomography as well. We also developed the passive local earthquake tomography on different scales, on scales of a few kilometers and on scales of 100 kilometers. So this is the same algorithm Lotus. And finally, this is the regional scale tomography, which was developed in the years of 90s. And it's also quite efficient tool to explore some mental heterogeneities. And I would like to start from this regional tomography code. And I remember it was in the years of 90s, just after the crash of Soviet Union, and I got the access to the international catalog of the IEC. And at some point, I realized that I can study any region of the world without asking permission of local authorities. If I use only earthquakes, located in this area, recorded by stations worldwide, I can investigate this region. If there are some stations here, it's good, but actually this scheme, for this regional tomography scheme is important that at least a part of the ray travels through our target area. And in this case, it doesn't matter whether there are earthquakes or stations here. In both cases, it provides us, it gives us the information about the structure of the, in this region. And it was, for me, it was a big fun to, after a completely closed society of Soviet Union, to open the world by this way. And for the Kamchatka region, you see that we use the earthquakes which are here. Of course, we have more earthquakes in Japan because there is much better observation system here, but still we have quite a lot of earthquakes here, very little stations here, but nevertheless, this information about the sources, about the earthquakes is enough to build seismic tomography. And I would say that subduction zones is a kind of benchmark for tomography. So if you developed an algorithm first, and if you go to subduction zone, and if you apply your algorithm for the subduction zone, and if you don't obtain such high velocity zone, it means that your algorithm doesn't work. So it's a kind of benchmark because we know the location of this high velocity zone from the seismicity. We know that this high velocity zone exists. So by this just a benchmark, we realize that this algorithm is working correctly. We observe this high velocity zone, which represents the high velocity slab. But at the same time, we can. The next step is to get some useful information. The presence of slab is not useful information. We know that the slab exists there, so it is just to check the algorithm. But after that, after next step is to analyze the details of this picture. And here we see that, for example, for the northern part of the Kamchatka and for the southern part of Kuril Island, the structure of the subduction slab is different. Here in the northern part, we see a kind of necking. So we see that the part of the subducting slab is here and here. It's a big drop, but in between we have some gap. It's a kind of necking, thinning of the plate. It means that the speed. Oh, sorry. It means that the speed of this, the rate, the descending rate of this part is faster than the rate of the plate. So it's a, it shows that in this area we have a mechanism of pulling that this part is pulling the subduction. At the same time, here in the north, in the southern part, we see that the upper part of the slab is thicker. So it means that here we have a speed of the rate of velocity of this part is slower than the rate of the subduction of the plate. So it means that there is a kind of coupling of the plate in this area. So here is a mechanism of push from the ocean. But this is not related to the volcanic topic. This is just a curious observation. What is really important for the volcanic observation is this feature, which is seen here. So here is Kamchatka, here is the slab at a depth of 150 kilometers. And here is the Aleutian slab, which is also there. We know about its presence from the deep seismicity also. But here we see a very clear slab window, very clear slab window. So we see that they are clearly separated from each other. And the border of this slab window is located just below the Silicic volcano. Silicic volcano is the last active volcano, is the northernmost active volcano of Kamchatka, which is very, very active and very, very dangerous volcano on Kamchatka. And we will return to this fact a little bit later. Now, let's talk about crust. So for the crust, to investigate the crustal structure, we have an algorithm of local earthquake tomography, LOTUS, which is used by many people in the world. And if you want, I would be happy to share this algorithm to explain how to use it. I did it many times for many people, and so I would be happy to make a kind of master classes how to use this code for local earthquake tomography. And I would like to show the results for the Klyuchevskoy volcanic group. The Klyuchevskoy volcanic group is a really unique place in the world. So you see that there are at least 10 big stratovolcanoes in this area. And all of them are different. So, for example, Klyuchevskoy is a huge volcano, it's the largest volcano in Eurasia. And it is a basaltic stratovolcano, and they produce moderate eruptions from the top and from the flanks. Bezymianny volcano, located only 10 kilometers from Klyuchevskoy, but the composition is completely different. This is a Silicic volcano, highly explosive, and this is completely different. Tolbachik, completely different. This is a Hawaiian type of volcano. Tolbachik, it consists of several volcanoes. So it is a Oster Tolbachik, sharp Tolbachik, Ploski is flat, and the Tolbachinsky Dol. This is a fissure area with a lot of cinder cone, with a lot of monogenic cones. So this is a kind of Hawaiian type of volcano with huge effusion of basaltic lavas, which propagate to dozens of kilometers with very high volume of basaltic lava. So, and Ushkovsky, for example, is a unique volcano. It is a dormant volcano now, but the volume of this volcano is more than the total volume of the rest of the Klyuchevskoy group. So each of this volcano is really unique. And how they are combined in such a small area of 80 kilometers only, this is a real reserve of different volcanoes. You can explore different type of volcanoes in such a small area. Udina, for example, also is a very funny volcano. It was appeared to awake at some point, and many people was afraid that this Udina volcano, which is a highly silicic volcano, may wake up and produce catastrophic eruptions. But fortunately, it calmed down, but it may produce eruption. Potentially, it may produce a big eruption in the future. And also, besides these stratovolcanoes, we needed to mention also a lot of monogenic cones, which are shown here by red dots. They form a kind of fissure, kind of fracture structures, fault structure. They highlight some faults here. We see them quite clearly. There is a Shevelic volcano. I already mentioned it. It is located above the slab window. And there is another active volcano. It's a Bezymianny volcano, which is quite active also volcano. And there are plenty of dormant volcanoes, like Nikolka, and there are many other volcanoes. So this is our camp in Tolbachik. So in 2014, we went to Tolbachik, and before our experiment, there were only 1, 2, 3, 4, 5, 6, 7 stations. And these stations were mostly oriented to investigate the central part of this group, the Klyuchevskoy and Bezymianny volcano, mostly Klyuchevskoy volcano. And in Tolbachik, there was only one station here. So Tolbachik was not explored before this experiment. And we deployed these stations, which are indicated here. There were some stations here deployed by Alaskan scientists, 6 stations, but they stayed only for 2 months, and they did not record much seismicity in that time, unfortunately. They did not contribute much into the study of this area. Okay, and this produced quite a lot of data. Together with the data of permanent network, we collected quite a good amount of data, which formed this satisfactory coverage, which was highest here and here. And based on this data, we produced a model of the crust for this different type of volcanoes. First of all, the Klyuchevskoy volcano is the largest volcano in this group, which is shown here. And below this volcano at the depth of 30-35 kilometers, we observe a big cluster of earthquakes. This is long period earthquakes, but nevertheless we can detect P and S waves from these earthquakes, and they are very high magnitude earthquakes, and they occur almost every day, several earthquakes per day with a high magnitude. So this is a very high seismicity area. And in this area we observe high VP and low VS. High VP means that there is a primitive magma which is coming there, and low VS means that this magma is in partially molten state, or with a lot of fluids dissolved. So this is an obvious signature that in this area we have a big magma reservoir. Then we look at the seismicity, and the seismicity here in this area, and we see that the seismicity forms a kind of the vertical line. It is aligned along the vertical line here, which starts from this deep reservoir and ends with the Klyuchevskoy volcano. In the intermediate part, we see some changes of VP-VS ratio. This is VP-VS ratio. At some depths, it is different, but nevertheless, the seismicity shows us a clear indication of a kind of the straight conduit, which brings magma from this high pressure reservoir to the top. And this high pressure reservoir serves as a kind of, the pressure in this reservoir is enough to bring the basaltic magma to the surface. So the Klyuchevskoy volcano has its own personal pipe that delivers magma from the mantle. If you look at the Tolbachik volcano, the structure appears to be slightly different. So you see some linear structures like this, and these large structures coincide with some seismicity. Black dots are the seismicity. And we see several zones of low velocity, which with high seismicity, and also in the map view we see that the kind of structures like this. So we see the structure here and the structure here, and we know that the main stratovolcanoes and the monogenic cones are aligned along these lines also. So this structure, this low velocity lines, they correspond to some fracture zones that exist in the crust, and these fracture zones are the pathway from the basaltic magma to go up to reach to feed the Tolbachik and other volcanoes of the system. If you look in general, we see that for three different types of volcanoes, for Klyuchevskoy, for Bezymianny, and for Tolbachik, there are different type of feeding system. For Klyuchevskoy, we have a straight vertical pipe that delivers magma to the surface. For Tolbachik, we have a system of fractures, and there are several fractures. One fracture comes from the same reservoir as here. You see that it follows here, and another fracture it goes from another direction, And actually, in this Tolbachik dole, in this Tolbachik fissure, there are several geochemical evidences of different sources, deep sources of magmas in different segments of these fractures. So this findings is supported by geochemical observation too. That there are two different sources for the magma from different part of the mantle. But this observation gives us only the crustal structure. It doesn't give any information about the mantle structure. And in this case, the mantle structure seems to be very important, because we needed to know where this magma comes from for Tolbachik. This magma, it might come from this reservoir, but this for the deep source of this path, we don't know anything. So we needed to get more data, and with this data that we collected during this campaign, we cannot get any information about the deep structure. And to explore the deep structure, we deployed another network, which will be shown in the next slides. And this scale is oriented to investigation of the mantle wedge beneath Kamchatka. So this is another experiment which was initiated by several institutes, including GFZ Potsdam, including Institut de Physique de Globe de Paris, and several Russian institutes. So we collected quite a lot of seismic stations from different places. In total, we have 100 stations. And this is, I would say that logistically, this was extremely difficult regarding the political reasons, regarding the bad weather, regarding the bad road conditions, and the very big expenses of this network. I think it was one of the most difficult campaigns that occurred in many different parts of the world. Finally, we built this network, and this network provided us quite a good ray coverage based on including the seismicity in the slab and in the crust. So I would say that the ray coverage in this case is compatible with well-studied regions like Japan or Alaska or other places, which is like a miracle for this area, which is extremely difficult to access. And I would like to show some results very quickly. So first of all, I would like to see how fluids migrates in the mantle wedge. The most efficient is to show the ratio of VP-VS ratio. The ratio between the VP-VS ratio is most sensitive to the presence of fluids. In the horizontal section, we see the same anomaly of high VP-VS ratio at a depth of 35 kilometers, and this anomaly is located right beneath the Klyuchevskoy volcano, which is exactly corresponding to the data to the models that I've shown before. And how it looks at depth. So we see that there is a slab here. We know the location of the slab from the distribution of seismicity. The shape of the slab is well constrained. And here we see at least 3 points, here, here, and here, at the depths of 100, 120, and 150, where we have such linear anomalies of VP-VS ratio that corresponds to different phases of phase transitions at the slab that produce some fluids. And at some depths, they join, and they form the whole area, the whole flux of fluids that come to this famous anomaly of high VP-VS ratio beneath the Klyuchevskoy volcano. So this, in this case, we have a straight, more or less straight path from the slab to this anomaly that fuel this anomaly. Let's look at what happens beneath Tolbachik. We see also the same structure. We see 3 flows at the depths of 100, 130, and 150, but they do not need each other. They are dispersed. They don't produce a joint flow. They don't produce a joint magma reservoir here. So the conditions of magma generation beneath Tolbachik is completely different. But if you look at this section along, which passes through Klyuchevskoy and the Tolbachik, we see that this anomaly, which is here, is spread along the crustal border, crustal boundary, toward the Tolbachik. So this path, path that was observed directly beneath Tolbachik is coming from the same reservoir, but which is spread laterally along the Mocha interface. Okay, so this was a VP-VS ratio. It's interesting to see the VP and the VS anomalies in this case. So we see that this is a depth of 50 kilometers. We see that at the depth of 50 kilometers, we have this huge anomaly of low VP and some anomaly of high VP. And in the vertical section from Shevelic to Bezymianny, we see that this anomaly has a kind of mushroom shape. So we have a kind of tail and some lateral extent of this anomaly. And the Klyuchevskoy group is located here. And if you look at, again, to this original model, which was here with this slab window, we see that this tail corresponds exactly to the place where this slab window is located. So we have a completely independent data, completely independent scales that complement each other. So we know that below Shevelych, there is an ascending floor of the asthenosphere. Then it meets some border of the crust, and then it spreads laterally toward the Klyuchevskoy group. Then it meets a big floor of fluids that was shown by the previous ratio, which produce such an active and diverse activity of volcanoes in the Klyuchevskoy group. There is another point which seems to be interesting, for which you may beat me as I don't know. So if you look at the composition of the volcanoes, so there is a low velocity and high velocity, and the composition of volcanoes is shown by the colors of the name. So for example, Bezymianny, Zimina, Udina, Tizimin, Zarechenskiy, and Shevelych are the Silicic volcano, which is a Silicic volcano, explosive volcano. And if you look at the Nikolka, Tolbachik, Klyuchevskoy, Kamchatka are basaltic volcano. And most of the monogenic cones are also basaltic. So there is a clear correspondence that basaltic volcanoes, mafic volcanoes corresponds to high velocity. And felsic volcanoes are located above the low velocity. Why is so? I propose a kind of very simple model. So if we have a hot mantle, it hits the crust, and the crust becomes ductile. And in the ductile material, we have a kind of diapir ascending, which is very slow. And inside this diapirs, we have a separation of magma from mafic to felsic. So we have long time of migration when this magma is produced, the silicic magma can produce. In the case of cold mantle, the crust is also cold, and we have a kind of fractures that form very fast. So the formation of fractures is very fast in the brittle medium, and the basaltic magma can reach the surface very quickly without any separation. So this might explain this difference between these two types of volcanoes. And the final example that I want to show you is a local scale. It's a scale of a single volcano, just an uppermost part of the magma reservoir, which is located just at the depth of a few kilometers, which is mostly responsible for the eruption activity. This is a case of the Bezymianny volcano. So this is a case of the Bezymianny volcano, which is here. And this is a Bezymianny, which is one of the beautiful volcanoes, one of the most interesting volcanoes that I like very much. So I love really this volcano. And this volcano, before the year of 50s, it was considered as an extinct or dormant volcano. And there was a story about one PhD student, and the chief of this, the supervisor, just given to him this volcano because it was just the most simple case which could not produce any eruption, and to study this volcano just in the year that she explored this volcano, this eruption occurred just in this volcano. So before this eruption, it was like this, and just after eruption, half of the mount was destroyed. It was very similar to St. Helens eruption with the sector collapse, and there were several episodes, and the blast rejected the ash up to the altitude of 35 kilometers. So it was one of the strongest events, volcanic eruptions on the Earth in 20th century. So, and now since that time, every year the volcano produces some small-scale eruptions and some extrusions and explosions. And slowly it produces the cone, and the altitude of this cone becomes higher and higher, and almost reached the altitude that was initially before the main eruption. And in 2017, we went to this volcano, to Bezymianny, to deploy a seismic station on the flanks of this volcano. So there are some permanent stations. So you see this is permanent 1 station, 2 stations, 3 stations. And these stations are very good there because they produce information for forecast this volcano. This volcano is very well forecasted. So almost 100% of the eruptions are forecasted by the geophysical survey. But at the same time, there is no seismic station in close location to the volcano. And we deployed the stations here. At the same time, we deployed also some video camera with Thomas Walter from GFZ. And also there was some petrological survey in this area. So we collected some samples. This was one of my sons who did it there. And it was in December, it was in the middle of winter, so we deployed our station in the summertime. And from summer to summer, it is impossible to reach these places. So we were in December and we looked at the images and we got this video from this volcano. And we see that this huge eruption, very large eruption, I would say, for only 30 minutes, this cloud reached the altitude of 15 kilometers. 30 minutes, you see the clocks there. So can you imagine what was the pressure to push all of this ash, the amount of gases that was rejected from the ground? And for such a short time, they brought this cloud to such a big altitude. And after that, it is ended. So we were quite excited by this information, but we were scared because this eruption could destroy our stations, could cover by pyroclastic flow, and then we came again, as you see that the Beza, this Mi-8 helicopter, which is absolutely crazy machine. And finally, this is a station which was located just 700 meters from the epicenter of the explosion. We expected that it should be covered by pyroclasts, but when we saw the lamp which was blinking, this was absolutely happiness of us, because it was not obvious. And we saved all stations and they collected unique information. If some of you is interested to use this information, I would be happy to provide this information, because there are not many cases in the world when the records were performed so closely to such strong explosions. Okay, what we recorded there. So I already said that Bezymianny is in normal life, it is a quiet volcano. So in normal life, it doesn't produce any seismicity. If you look at this is the depth and this are days before the explosion. And you can see that the average background of seismicity is approximately 10 events per month, even less than 10. Then there was one small cluster, but with quite strong events that are detectable, that are with real magnitudes events, which occurred at the depths of 6 kilometers. But if the altitude of the volcano is 2 to 3 kilometers, it's a depth of 8 kilometers below the surface. Then there was a gap without seismicity, and finally, 1 week before the earthquake, before the eruption, there was an exponential increase of seismicity, and such an exponential increase is the most solid forecast precursor. So they can really identify the hour of the beginning of the eruption. So this is for most of the eruptions of the Bezymianny, they observe such kind of increase of seismicity. And in total, we picked more than 500 events, which was enough to build some seismic tomography corresponding exactly to the moment of the eruption. So what we have observed here, it's a VP anomalies, DS anomalies, and VP-DS regression. This is in horizontal slice and in the vertical slice. What we can observe is a almost perfect anti-correlation of P and S anomalies. See, low velocity, high velocity, high velocity, low velocity, high velocity, low velocity. And we observe a very clear image of the VPVS ratio, low VPVS ratio, high VPVS ratio, and high VPVS ratio. And each of these features has some very clear explanation. So the VPVS ratio is very sensitive to the presence of fluid. If the fluids are liquid, it produces a low VPVS ratio. So it may represent the partial melting or the content of fluids, the liquid fluids, if they are dissolved in the magma. So this area is the area of magma reservoir, which was here. And there was also the petrological evidences that the magma reservoir, the shallowest magma reservoir, should be located here. But what was the most amazing here is that this anomaly of 1.5 of low VPVS ratio. And low VPVS ratio occurs if the rocks behave like a sponge. So they have very low VP because they have a very small compression resistance. It's like a sponge because they are filled with gases, so you can easily compress them. At the same time, they keep some rigidity in the shear direction, so they have a normal VS. So this was observed in many different volcanoes that produce a lot of gases, like Nevada del Ruiz or Gorelli. They always show such kind of low VPVS ratio. And this low VPVS ratio represents the reservoir, which is which hold the gases that was ejected during this eruption. And in general, we built a scenario based on different observations, including the seismic tomography, distribution of seismicity, also the ground deformation, which was produced by Thomas Walter, and also petrology. And based on all of this information, we produced this scenario so that before 8 weeks, 40 days before the eruption, all fluids were contained in this middle crustal reservoir. And we saw this middle crustal reservoir in our results of larger scale tomography. We saw that below Bezymianny, at this depth, there is a middle crustal reservoir with low velocity. At some point, the saturation of this reservoir becomes too high, and some fluids start to escape from it. The escape of fluids, it produces some hydrofractures that are expressed as exhibited as a seismicity that occurred 45 days before the eruption. After producing the pathway, these gases freely come to the shallowmost reservoir, and finally it was stored here for 45 days. It produces the higher and higher and increased the pressure in this reservoir, and while it starts to be too high, it starts to produce some system of cracks that finally produced this main conduit that brought the gases to the surface. And at the same time, for this network, we produced a kind of an ambient noise analysis of ambient noise. So for each day, we made a noise correlation for the whole area. This line corresponds to the eruption, and you see that we have some coherent phases that are observed throughout the observation. And we explored this part of the coda wave, so the longer time, and this longer time observation, it allows us to monitor the changes of velocities in our system for different frequencies. So we have low frequencies that are more sensitive to deep patterns, and we have high frequencies that are more sensitive to the shallow patterns. So we see that these are the curves corresponding to changes of velocities for different frequencies. And we see that, for example, for the shallow part for 1 to 3 seconds, we observe this curve, and for the longer periods, we have a different curve. And in general, this behavior corresponds to the scenario that we proposed based on the other observations. So indeed, in case when we have penetration of fluids in this area, we have a decrease at low frequency, and we don't have any changes in high frequencies. At the same time, when there is a compaction of this area due to high pressures, we have an increase of velocities at shallow depths. And finally, before the eruption, we have an abrupt change, abrupt decrease of velocity that we observe here, but we don't have such a good resolution because it was just in the order of several days. So this was the solve that I would like to show. I have a lot of different results, but this this talk it summarizes most of the results obtained for the Klyuchevskoy group, which is a unique group of volcanoes. And we claim that we systematically explore this group, and therefore this group becomes one of the best studied regions in the world. Systematically studied, it means that we have results on different scales, and each of the scales contributed to bring some bricks to understand the general behavior of the system, how the magma is produced at different depth levels. So, and all the information about this talk is contained in this article, which is in Russian Geology and Geophysics, but it is available in Russian. So all this information is available. Also, I would like to say again that all the data, all the algorithms, all the models can be provided to any person. So I would be very happy to collaborate either on the Kamchatka topics or on other topics in the world. So this nice picture is from the Paramoshir Island. This is Okhotsk Sea and the Alait volcano, and this is absolutely amazing place. So if you come here, I would be very happy. So thank you very much.
Well, many thanks, Ivan, for the nice presentation. Are there questions in the audience? Yeah.
I would like to ask you, you connected some property, some value of VP velocity, VS velocity with some different, that pictures with some different content of fluid and different properties of fluid. I think it should be also sensitive to the attenuation of seismic waves. So did you study not only kinematics but also dynamic of the data?
Actually, we have some people in my group who study attenuation, and we have some results on the Koulakov volcano, for example, or on Harat Lunair in Saudi Arabia, but not for Kamchatka volcano yet. We are working on it, but unfortunately it is a little bit slow. And yes, attenuation is a very important attribute that should be also included. For sure, yes, it is very important. For example, it allows us to distinguish between a gas-saturated area and just rigid and dry rocks. Only by velocities we cannot distinguish these two cases, but with attenuation it is possible to distinguish very easily.
Thank you. Further questions? Yes.
I understand it's a very difficult field, but is there any chance to do surface deformation monitoring, like GPS stations or something like that, to correlate with what happens with the volcanic processes?
Yes, this was exactly the case of the Bezymianny volcano. Unfortunately, I did not show the pictures here, but it shows exactly, according to this scenario, we could see the places where it is inflated and deflated, so we could really observe the observation of this process. But unfortunately, there is a period of 11 days of satellite passing in this area. So unfortunately, we could not see the changes every day, but during 11 days, with 11-day periodicity, we could see these changes, and it matches the results that we observe here. So for sure, for example, for Kharat lunar year, for Aleutian Island, also there is a nice correlation between tomography and INSAR observations. And also for Okmok, we did also the comparison of the. So this is for sure very important. Yes.
More questions? Otherwise, I'll give people some time to think and ask one myself. We showed for Klyuchevskoy volcano that there was this more or less vertical conduit that came from depth of like 30 kilometers to the surface that you outlined from hypocenters, I think, of LP events, right? Yeah, exactly, this one. What surprised me here is that this conduit doesn't seem to have a velocity signature.
Because it is too narrow.
Okay, that's the answer. So you think it should have one, but you don't have the spatial resolution to actually resolve?
Yes, it is too narrow. It's an order of less than 1 kilometer, and for such depths we cannot see it. Okay. And these features are related to degassing, to some processes inside of magma. And also it is mixed with some surrounding rocks, so it becomes more and more silicic at the surface. Yes.
Ivan, what is the resolution of this tomography and how is your reading? Because this vertical paths go through this heterogeneity, or what? I don't understand.
So in our algorithm, we use the grid, which is a priori smaller than our resolution. So we do it explicitly to avoid any bias related to the grid geometry. So the grid spacing should be smaller. So each anomaly should be based on several grids. This is our point, that we really believe that it is important. For the resolution, we do the resolution test like checkerboard, and for each of the structures, or we can make a kind of free-shaped anomalies. And for this study, we provided a lot of tests that have proven that each of these anomalies are valid. But for sure that for 1 kilometer size, we cannot resolve in such depths, unfortunately.
For example, is grid for this particular picture on the right side?
Oof, I think it was a half kilometer. Some half kilometer grid. It was, I don't remember exactly, but it was quite a fine grid spacing. So my point is to use a fine grid spacing to avoid any bias related to the grid geometry. But it doesn't matter the spacing, because here we play not with the spacing. The resolution is determined by some damping parameters, not by grid spacing. Grid spacing, it's a kind of continuous parameterization.
But understand the picture, it's necessary to know this reading.
It doesn't matter if it is a half kilometer or 1 kilometer, or unless it is it becomes larger than the size of anomalies. When it becomes larger than the size of anomalies, it becomes critical, the size of the grid spacing. When it is smaller than the size of anomalies, it doesn't matter. If it is 100 meter, half kilometer, 1 kilometer, it should give the same result.
More questions? I don't see any. If anybody wants to speak to Ivan and discuss either what he has shown here or some other results that he was hinting at but didn't bring up in this presentation, you can do it either, I guess, now, because probably now there will be a half hour of break.
We have a break.
So we can be back there with some coffee and water, I guess, and you can talk to him there. You also have the chance to come to Uchizi after the second talk, which this little expedition should start at something like 4:30. And I think it's not really defined yet, but there might also be the opportunity that you could also be around for part of tomorrow. Or is that...
Yes, I'm completely available. So I came to the end of this week. So I would be happy to maybe to show how the algorithms work, to show some technical details, how to run the surface wave tomography or body wave tomography. So if somebody is interested, I would be happy to come tomorrow and to work on some real data if you have.
Okay, so if anybody's interested in that, either contact me directly or mention it to me and we can organize.
I have a Czech telephone number, so you can join at any moment.
Okay, otherwise, thanks a lot for questions and for the attention, and thanks a lot for the